everyone. Welcome to Expert Talks Online. If this is your first time with us, welcome. Although I do recognise a few names, so thank you for joining us for those who have come back again. Equal Experts is a software consulting company, and one of our passions is to make sure that we give back to the community by running events like this. My name is Tony Nguyen, and I'm the Transformation and Delivery Principal for APAC, and I'll be hosting you this evening. Our speaker today is Paul Browen, who is joining us online from Sheffield in the UK. Paul's been a technical lead for us for about 2 years now, and we are very lucky to have him because if you see him suddenly disappear in the middle of his talk, there is a small chance that he's running off to the hospital as he and his wife are expecting a baby at any moment. Today, however, whilst we still have him, he's going to be here and he will be talking about machine learning. We're going to have some Q&A time at the end, so if you have a question, there is a Q&A panel you can pop up at the bottom of your screen and use that to pop the question in there, and we'll hit those at the end. On that note, I'm going to hand over to Paul.
Great, thank you, Tony. And thanks everyone for coming along. It's a great pleasure to be talking to you today. We're going to be talking about machine learning. As the synopsis said, this is an introductory talk, so we'll be sticking to kind of like fairly classic techniques, but we're talking about why we do machine learning. Then we'll move on to how we build machine learning models and the machine learning workflow, how we deploy them. That'll take us into the challenges that we face when we are trying to use machine learning models and build them. And that leads us into how we can avoid some of those challenges, because as you'll see, some of them are quite big obstacles to get over. Just a couple of housekeeping notes. So as Tony said, any questions for the end in the Q&A, if that's okay. There's also some participation in the talk. So you'll be asked to raise your hand, use the raise hand function in Zoom, because there are a few questions that we'd like to get you participating on. If you do have an answer, please just raise your hand. And lastly, there will be 2 polls running towards the end of the talk. So I'd love to get you all involved in that and see what you think. You'll be sitting in a product owner seat for machine learning based products. Get your opinions on those. Okay, so talking about how machine learning works, I think it's a good idea to start before we had machine learning. And if we go all the way to 500 years BC, we see an equation like this. So this is the first raise your hand option. So if you could hit the raise hand button, if you know what that equation is and what it's for, please. Just give you a few seconds. Do we have anybody with that who's raised their hand?
Got 4 up.
4 up.
4 or
Excellent.
5, yep.
Excellent. Who's answering?
They're all muted, Paul.
Oh, Sheila, could you unmute someone to answer, please? Hi, Amanda.
Quadratic equation?
Nearly. It's Pythagoras theorem.
Close.
Close, yeah, very close. I can see exactly what you did there. It's similar, isn't it? Yeah. This is. Do you know what Pythagoras theorem is as well?
Yes, I do. Sorry, you got me there. It was.
Yeah.
You got me there. It was too quick.
Go ahead. Do you want to just tell us what that is then, Amanda? Okay, she's muted again. I will. So Pythagoras theorem if we know the length of 2 sides of a right-angled triangle, we can work out the length of the 3rd side. And that's been with us for a long time. And you see how that would be useful for all sorts of things, for building stuff, for navigation, even for astronomy. So you can see why that was an interesting problem to solve, even back to 500 BC. So I'm going to ask you another one now. But I'll give you some context for this. So we're going to look at 3 equations like this to look at how we solve problems before we did machine learning. Then we're going to look at some problems that we use machine learning to solve, and we're going to compare them. That's what we're doing here. So think about what makes these different to the next equations. So the next one is this. So does anybody know what that equation is? If you do, pop your hand up. Just give you a few seconds.
I think you've scared them off after the first one, Paul.
Peter Cook.
Hi, Peter.
Hi. That future value equals present value times 1 plus.
Yeah, that's exactly right. Thank you, Peter. So yeah, this is if you have an asset like money in a bank account, and you have an interest rate, and you want to know how much your asset is going to be worth in 10 months' time, you can use this equation to work it out. Thank you, Peter. Thank you, Amanda, as well, for having got the first one. Great. So I've got one more of these, and then we'll move on to the machine learning problems. So this equation. Does anybody know what that equation is?
Martin?
It's energy equals mass multiplied by the square of speed of light.
Yeah. Yeah, perfect. Yeah, this is Einstein's mass energy equivalence, as you say. Yeah, that's a really recent one. That's only been around for a few tens of years. So we've been solving these problems for a long time. The one in the middle, we've actually got records going back to 2000 BC. The Babylonians knew about how to figure out future values of assets. I guess money's always been important. Great. So all these equations are an example of problems that we solved before we have machine learning, and they're all formulated in a similar way. So we have something that we don't know, which we call y, and we have some things that we do know, which we call x, which can be one or more things. And we have what we want to know is the relationship between the x and the y. So we describe that as f in this equation here. So you get y equals f of x, and I'm sure you will remember that from school. So bearing that in mind, and bearing in mind these equations and how we might have solved these problems back in the day, let's think about these new questions. So imagine we have we want to make recommendations for music. So now my X has become Motorhead and Metallica. I like Motorhead and Metallica, and I want to know another artist I'm going to like. So what's the relationship between Motorhead and Metallica and an artist I'm going to like? So that's a different kind of problem, but what makes that different to the problems we had before? Another example, so if we have emails coming in for quite a while now, since we've had email, basically, we've been wanting to figure out whether or not the email is spam. So given an email, is there some relationship between the email and whether or not it's spam? So does it contain the phrase Nigerian prince, for example? Could be an indicator that it's going to be spam. Last example, and again, we've been trying to do this with computers since we had them. If you have a sentence in English, is there a way to translate it into a sentence in Italian? So if I say, I love you in English, I'll translate that into ti amo in Italian. And on this last one, just to kind of illustrate how far back we've been doing this, an IBM researcher called Frederick Jelinek, back in the 1980s, had been working on machine language recognition and translation for a while. And he's attributed a quote, which is reasonably famous. You might have heard of it. He said, "Every time I fire a linguist, the performance of the speech recognizer goes up." And what he was saying there was just that humans trying to write rules for speech recognition did not perform as well as using machine learning-based techniques. So, on the first, in the left-hand column here, you've got the problems we were solving to start with, and then the second, we've got the problems that we think we probably need machine learning to solve. So, can you raise your hands if you have any ideas what makes these two problems different? What might make them different in such a way that machine learning might be a good solution for the second set? So any ideas at all? Just raise your hand.
Martin?
So in the first one, you have to solve an equation. And in the second one, you need some kind of statistical analysis.
Yeah, that's a good one. Yeah. Absolutely. So you're saying that there isn't a simple equation for the second set in the same way as there is for the first. Is that what you're saying?
There may be, but it may be very difficult to find one, or it could be extremely complicated.
Yeah, that's really good. Yeah, thank you, Martin. Have we got any other suggestions as to what might have been different? I can think of a couple more things.
Benedict popped his hand up.
Hello.
Hello.
Yeah, I think for the second one, it's more about prediction, whereas the first one is just calculating it and getting an answer.
Yeah, that's a good observation. So you're trying to predict something where there isn't like an obvious answer in the same way for the first one. Yeah, it's a good observation.
Yeah.
Thank you, Benedict. That's great. And we'll take one more.
Gurjit?
Hi, am I audible?
Yes.
Hi, yes, I can hear you.
Yeah.
Hi. I think the sides of a triangle is if the customer touches any particular side of a triangle and the algorithm recommends them a particular sort of music, and every time they touch a certain side, that genre is played. The first one would be that, but that's a wild guess. The second one is much more easy. It's a catchphrase which algorithms detect in an email. So if it's a compound interest or free lottery, these phrases, if the algorithm picks up, most likely it's supposed to be a spam.
Oh, okay. I see. I see. So
That's
you're
about-
relating the things directly from the first to second column. Okay, that's interesting. Go ahead.
Yeah, that's
Great.
it. That's about it.
Thank you. Good. Yeah, I've not. Nobody's tried to do it before. That's really interesting. Thank you. Yeah. So the three things I had in my list, or the other two things that we mentioned, are really interesting as well. Are we had relatively simple relationships, which I think Martin's told us to start with. The second thing, which I think you've all hinted on, is that there's a right answer rather than it being subjective, a matter of opinion, for the things in the first list. Given a triangle with two sides of a certain length, there's only one answer for the third side, whereas there could be many answers as to which artist to recommend for certain preferences. And the third thing that I would suggest is that the answer stays the same over time. So the amount your asset would have been worth with the compound interest equation would have been the same 2,000 years ago as it is today, whereas spammers are improving their techniques all the time. So a good algorithm to figure out whether an email is spam in a year's time might be different to one today. So thank you all for participating in that. That was really good. Great. So hopefully you can see that there is a difference between things that we've solved before machine learning and things that we've solved with machine learning now. It's to do with context and things staying the same over time and so forth. So that leads us on to machine learning. So Andrew Ng is one of the founders of Coursera, a massive kind of an online learning resource, which I'd definitely recommend taking a look at if you've got time. And he wrote his first machine learning course. And I quite like his explanation of what machine learning is. There's lots of different sort of quotes that you could use for what machine learning is, but this one I think is quite good. And he says it's the science of getting computers to act without being explicitly programmed. So traditionally, when we write software for computers to execute, software developers will go and basically write rules in the form of code. So they will they'll use their own domain knowledge, they'll talk to experts, and they'll come up with a set of rules and encode those in software. And what we found is that's good for problems like Pythagoras theorem. It's not good for problems like spam recognition or for language processing. So we found that actually taking lots and lots of data, taking out a general algorithm and lots of data and applying computers to that can give us a better way of figuring out what this relationship F is than just taking people and having them write rules. And that's the kind of key insight behind what machine learning is all about. With that, we'll actually go into some machine learning stuff. So there's a few tasks that machine learning can undertake, but they fall into some general categories. So there's a big category is classification. So here's an example of classification. If I showed you this photo and asked you, is it a cat or a turnip? You could tell me which one it is. And getting a computer to do a similar sort of thing is a classification task, which we could solve with machine learning. The other basic task is regression, which I didn't know what that meant until I started doing machine learning stuff, because I called it something different. But it's basically, instead of trying to figure out what class an object is in, we figure out the value of something. So if you took your house and you wanted to know how much it would be worth if you sold it, that would be a regression problem because you're trying to predict a number rather than a class. There are other kinds of problems. Recommendations is the third, I think, is a third kind of problem. So having a machine learning algorithm make recommendations to you. And the fourth, and I think this kind of caps it off, is unsupervised learning, something like trying to detect structure in data. But we're going to focus on regression for this talk, just to be able to work through an example of a machine learning algorithm and how it works. So how much is a house worth? So what we're going to do is actually take a data set which is available publicly. It's I think it's from Ames, Iowa in the US, and it tells us the sale price for a house, along with a whole bunch of properties that the house had. So if you imagine an estate agent would have gone in and surveyed the house, they would have measured things and they would have given their opinion on things, on the quality of the rendering and things like that. And they basically came up with these large sets of data for each house, of which I'm going to take two properties here, just the lot area and the basement square foot. And then when the house sold, they recorded what the sale price was. So we have this big data set. So phrasing that in the manner that we had earlier. So our Y now is sale price. That's what we don't know for a house that we haven't seen before. We don't know the sale price. We can go and survey it and get the lot area, the basement square foot, etc. And what we want to know is the relationship between those two things. And this is the kind of problem that is a classic kind of, this is how we use machine learning sort of problems. That's why we're looking at this. I'm going to kind of rephrase what was on the previous slide in slightly different terminology, just to introduce you to some machine learning terminology. So putting this in more mathematical terminology. So we have y equals f of x again, and in the table below, sale prices become y. And we have, what I draw your attention to here is the fact that x is uppercase. So if you use libraries, if you do go on from here and use libraries like scikit-learn, you'll find that they have examples and documentation where some variables are uppercase and some are lowercase. Uppercase just means that there are multiple values in here. It's a vector, it's an array of values. So uppercase x means that you get x1, x2, x3, as you can see below, but they map onto the columns in the same way. It's just a spreadsheet, really. Last example of alternative terminology. So machine learning people would say that we've got a target variable, which is sale price, that's y. And now we've got an array of features, which is the x, and it's basement square footage and lot area in this case. So machine learning people would use the term features and target variables. We'd use examples or instances for each of the rows of the spreadsheet. And when I say features here, I'll just mention something called feature engineering, which will not dig into any detail here, but it'll come up a couple of times. So these are raw features, these are the raw values from the data. But what we can also do is manipulate them. We can multiply them together. We'll have to do some manipulation because there might be some nonsense values in there. There might be some zeros for lot area. So we might need to handle that, or some missing values. So feature engineering will come up a couple of times. It's a really deep area, but you don't need to understand that too much to understand what's actually going on. Given that data set, we have features, we have examples, we have a target variable. We can now use the machine learning workflow, and every machine learning process that I've ever come across uses basically the same workflow in one form or another. Your first challenge is to get your data, to get examples. Your next task is to train your model. Your next task is then to evaluate the model, see if it's any good. So you might have split your examples up into a set of training data and then a set of test data, and you would show the test data to your trained model to see how it performed. Did it make good predictions? You can, if your model did not perform well enough for you, then you could try again. You could get some more data. You could change the kind of model that you're using. You could do some feature engineering and try again and see if you get the kind of quality of results that you want. We will go into that evaluation part in a little more detail later. Once you're happy with your model, then you can deploy it. You can put it in front of your customers or whoever it is who's going to be using the model. And as part of that, putting it in front of the customers, you may well harvest new examples from those customers and add them to your data set so that you can actually keep your model up to date and getting better over time instead of getting worse. So that helps us solve that problem of the answer changing over time that we talked about earlier. So that's the machine learning workflow. As you'll see later, there are some tools that actually kind of implement that for you, and you can skip some of the steps of setting all this stuff up yourself. Is machine learning easy? You might get the impression so far that maybe machine learning is easy. I think what I'm trying to get across is that the intuitions behind it are really easy to understand. They're really straightforward. There are some big challenges, though, when you actually try and apply machine learning, and that's what we're going to start digging into now. So the first thing that we have to do when we're using machine learning is getting data. It's unlikely that you're going to be using a public data set, although it's possible, certainly for research purposes, you might be using a public data set. But it's more likely, I think, that you'd be using a data set that you have in your business, that you have and other people don't have. And in that case, either you have that data to start with or you don't have it and you need to produce it. So you might need to go and get that data. You might need to ask your customers for permission to get that data to comply with regulatory requirements around privacy and security. So right at the very beginning of this process, doing the right thing and elements of ethics and regulatory compliance come in, getting your data, getting it labeled up correctly. Well, let's assume that you've got your data. You've either already got it or you've collected it, and it's all there ready to go. Your next job is to clean the data up. So I mentioned earlier about your data you might have nonsense values like a 0 for the area of the plot of land a house is on. That doesn't make any sense. Or it could just have missing values. So there might just be rows that just have missing values in columns. So how do you handle those? Do you allow those values through? Some machine learning models can't use, they have to have numeric values in all the columns. So the regression model that we'll look at will have to have numeric values in all the columns. So you've got to make some decisions about how to clean the data up. And there's trade-offs, pros and cons to the different approaches there. As I say, that kind of leads into feature engineering, and that's a whole big area in its own right. But let's assume that we clean our data up and we have a data set that will now work with our machine learning model. The next job is to train it. So we'll need to choose the kind of model that we actually want. We'll need to think about some other important choices here as well. So we'll need to decide whether or not we need to explain the decisions that the model is making. And we might need to go back and tune our feature engineering to suit the kind of model that we want to use. We'll pause here and we'll have a look at what the data might look like at this point. So what you're looking at the moment is the data set that we looked at earlier. So we have the lot area for the houses is on the x-axis at the bottom, 50,000 square feet, 100,000 square feet. On the y-axis at the side, we've got sale price in dollars, $100,000 up to $800,000. And each dot, each blue dot, is one of those rows of the spreadsheet. I'm sure you've all done all this sort of thing before. This is just done in Excel, so or a spreadsheet application. So there's no magic machine learning happening here. So what I want you to think about for a moment is if you were going to draw a line through that data, kind of a line of best fit that you were going to use to predict new house prices from lot areas, where would you draw a line through that data? I'll just give you a moment to just visualize where you think the line would go. Okay, and I will show you what the line of best fit is through that data according to Excel. And I'm guessing that's probably not where you would have drawn the line. So for me personally, it would be a lot steeper and it would be shifted over to the left so that it went through that big mist of points that kind of is quite close to the y-axis. But what's pulling it across is these kind of outliers, if you like, these data points that are way over to the right compared to the rest. It pulls that line across. But it does give us a line, and it gives us a line that minimizes a certain error value. And the error you can see from I've drawn you an example of an error. It's a vertical distance between the line and the blue point. So that line does minimize a measure of error for all those data points. So that is a line of best fit according to that measure. If we were going to use it to predict a value, we would just look, say, at $100,000 on the x-axis, draw straight up to the line and then across to the y-axis, and we would get a sale price of around about $380,000 or so. So this is our model. So we have essentially sale price equals 2 times the lot area plus 158,000. If you look at the bottom, then that's back into that y equals f of x formulation. And as you can see, if we know the lot area, we can now work out a sale price. So this is a model. This is on a very basic machine learning model for house prices. But it doesn't look like a very good fit to me. So I'm going to show you a different kind of model because I'm going to bring in a second variable. We're going to bring in the total basement square footage, and I'm going to use a different kind of model that's a bit more interesting, I think, because we probably all did line fitting at school. So how about this? So what you're looking at now is very similar. You may not look it, but the x-axis is now lot area, same thing as before, but the y-axis is not value anymore. This is total basement square footage going up on the left. So we've got 2 features now. Remember, there were 2 columns in the spreadsheet, 2 features. Each point is a row from the spreadsheet, and the color of the point, you can see a key up to the top right. The color of the point, the darker it is, the more valuable the house was when it was sold. So you can see this down to the bottom left, there's lots of kind of very pale colored points. As you move up through that big mist of points, you'll find them getting darker and darker. And some of the darkest points are just towards the top of that mist. You can see, I've called out a few just as examples. At the top, we've got a large plot with a huge basement. It's worth about $250,000. Over to the right, it's a huge plot with an average basement. It's worth about $400,000. And this really expensive property, more over to the left, is an average size plot, an average sized basement, but it's worth $1 million or in that sort of ballpark. So that's what data looks like with 2 dimensions, with 2 features being shown. And we're going to use a slightly different model. We can use linear regression with 2 features, but it's difficult to visualize it. So let's just have a look at the k-nearest neighbors algorithm. This is a machine learning algorithm. And what we would do to get a prediction from the k-nearest neighbors algorithm is that we would look at all the data points. So the red dot that I've drawn on the screen there is a new house that we've never seen before. We know what the lot area and basement square footage, so that's why it appears there. what we can then do is look at how far away all the other points are in this two-dimensional space. So just measuring the distance using probably Pythagoras theorem. There are some other distance measures, but we'd probably use that. Then once we've got the distances, we can work out how close, we can work out the set of points are the nearest k points. So we're going to use k equals 3 for the purpose of this example. And then we can use the average of those 3 nearest points to get a prediction of the sale price. So if you look at those 3 nearest points, they're all pretty similar in terms of color. So the sale price prediction you would imagine would be reasonably good for that, for that example. And I would certainly expect that the k-nearest neighbors algorithm would do better with these 2 features than linear regression did with the 1 feature before. We have to take my word for it, because what I did was actually run through a couple of machine learning algorithms. So we did a linear regression with 1 feature, and when you actually kind of run that algorithm and generate a measure of the error. Now what I'm using here, this MAE value, is the mean average error. So if you like, that is sort of the average error for all the data points versus the model. So for that 1 feature linear regression, the average error was $57,000. That was how far off it was on average. If you think about how those data points, so a lot of them are very close together, some of them are very far away. So that mean average error may not be a great estimator may not be a very useful estimator of the error. But we're going to use that for now, it's easy to understand. The k-nearest neighbor with the k-nearest neighbor algorithm with k equals 3 and 2 features, what we just saw, that brings that mean average error down to $54,000. So to be honest, it's not brought it down as much as I would expect. If we do a linear regression with the same 2 features, it brings it down to $46,000. So the linear regression with 2 features does better than the k-nearest neighbors algorithm against this data set. And just to round it out, there are 10 numeric features in that data set. And if I just add all 10 numeric features into the model and run linear regression, I actually get the mean average error down to $22,000, which is quite a big improvement over 57. So that's just here to give you an example of how tweaking some of these parameters, changing the kind of model can affect the quality of the predictions that you can make. But again, evaluation is another area where there's all sorts of things you can do depending on your use case. So that's an area that you could dig into if you wanted to look into it in more detail. Certainly, if you're going to build your own models, it's an area you'd need to look into. Right. So back to the steps. So the next step is actually deploying your model and making sure that it's safe to go out into the world. So there's 2 sides. So from the deployment point of view, we need to make sure that our model isn't going to bankrupt our company or fall over. So if it costs £1 to actually make a prediction, and we put it out on the internet and 1 million people come, then we could bankrupt our company. And if it takes 30 seconds to make a prediction, people might come and not wait. They might get bored and go away. So speed and performance, all those kind of standard performance metrics that we would use for software development and deploying services out into the world, they apply to machine learning products as well. I touched earlier about ethics and explainability. So some machine learning models like linear regression that you saw, it's quite easy to understand how they work. It's quite easy to explain how they make decisions. But, and the poster child for this is deep learning, deep neural network models. Some machine learning models are just not, it's not possible to currently explain how they make their decisions. They're a black box. The inputs go in, the decisions come out, and you can't really explain it. And if you're working in healthcare or finance, that kind of area, areas that have very stringent regulatory requirements around them, you may need to be able to explain how your algorithm works. If you know the European GDPR at all, which I appreciate this audience might not know it so well, there is an entire section in there about automated decision making and giving people the ability to opt in and opt out and so forth. And machine learning, I think machine learning fits very much into that automated decision making category. So it is often touched by regulatory requirements, and explainability can be one of the things that you need that might affect your choice of model. And the last slide on here is the big one, which is all about ethics. And rather than talk about ethics myself, I'm just going to show you some examples of that we have that hit the news where companies got this wrong. So we'll start with Microsoft, who on March 23rd, 2016, they released a chatbot called Tay Tweets. So this is on the internet. It was a Twitter bot. So people could just talk to it, and the innovation that Microsoft made was to have this chatbot learn from the things that people were talking to it. So it would learn about the world from the people talking to it. And as you can possibly imagine, within 16 hours, it had become, amongst other terrible things, a Holocaust denier. And this is only going back 4 or 5 years now, but it was pretty much towards the beginning of machine learning kind of hitting the mainstream. These days, I imagine a lot of folks would recognize that this problem could happen from putting something out onto the internet. We're a bit more familiar with it now, but back in the day, this did happen. Microsoft did take that tweets down and kind of fixed it, and I think it is actually still running today. I could be wrong. So yeah, Microsoft got this wrong. Niantic is the company behind Pokemon Go, which is, I'm sure you've all heard of it, incredibly popular augmented reality game. Well, I'm assuming that actually, certainly in the UK it is. Essentially, you can take your phone or device and you go out into the world, and you will find artifacts that you progress in the game. You'll find Pokemon gyms and new creatures to collect and things like that. And the news stories that were hitting the headlines looked a bit like this. And what happened, what people were finding was that in affluent areas, there were lots of these artifacts in the world. You could go out your front door and very quickly find all these things and progress in the game. But if you were in less affluent areas, which this is an American article, less affluent areas tended to be communities of color. Going outside your front door, and there was nothing at all, really sparse for these artifacts. And what had happened was Niantic needed to bootstrap Pokemon Go with some location data. So they used the data from a different game. But the other game was a lot less popular and tended to be used by kids from these affluent areas. So because of that demographic shift, they ended up with lots of artifacts in these affluent areas. But the demographics had moved for Pokemon Go. There were now lots of different people using it. And that's a subtle one, I think. That's one that I would probably have missed. I could imagine I could have missed that if it was me. So yeah, Niantic got it wrong there. Last one in this section. So Amazon decided to try and use machine learning to screen CVs as part of their recruitment process. And I'm sure we can imagine what happened next. These sorts of headlines were hitting the headlines because the system had learned that male candidates were preferable. And again, you look at it and you think, oh, yeah, obviously. But maybe at the time, maybe back in 2018, I think this was, maybe we wouldn't have thought about that. Who knows? But yeah, so Amazon also got this wrong. And every so often, these news articles are hitting the headlines. And there was one very recently that I'll touch on towards the end as well. But for now, it's time for the polls. So having looked at a few use cases as we have done for the last 3 sort of negative examples, and we looked at how machine learning models work, how you evaluate them, what I'd like you to do is sit in the product owner seat for an amazing new music recommendation product. A lot of machine learning models are based on statistics and probability, so they can give you a confidence when they make a prediction. So in that example we had earlier, we had Metallica and Motorhead, I think. The model could then give you predictions, maybe more than one prediction, and it could tell you how confident it was that it was a good prediction, give you a number between 0 and 1. So let's see how we use that. You are building an autoplay function using this music recommendation machine learning system. Sometimes your recommender is going to come out with a prediction that it doesn't have much confidence in. The confidence is low. So the question for you is, should your music autoplay system, should it play it anyway when the confidence is low, or should it stop and let the user choose what to do next? So the poll should be coming up in a moment if you'd just like to choose the option that you think. So we'll just give people a few seconds to make their choices. And there isn't a right or wrong answer, I think, for these. This is very much kind of your opinion and how you visualize the product. How are we doing?
Okay, so we've got, I think about half of you voted, so 66% have voted. Shall I finish it now? Give you 5 seconds?
Yeah.
2, 3, 4, 5.
Thank you.
Can you see that, Paul?
Yes, we can, yes. So hopefully everybody can see this, but just in case. So 56% of you said play it anyway, and 45% said stop playing and let the user choose. And that's great. I think I can see how you would reach either conclusion. It depends on how you're visualizing the products in your mind and what your goals are for that product in your mind as well. I definitely don't think there's a right or wrong answer here. So that's a really even split actually as well. That's really good. Okay, so we've got one more of these. It's a similar sort of context, but it's a similar problem but a different context. So now you are the product owner in a medical imaging company which is building an amazing new cancer screening system. Similar sort of problem. So your system looks at medical images, probably not a hand like this, but it could be, and it looks for evidence of tumors, cancerous growth tumors in the images. And this is a real sort of problem that machine learning has been applied to. Question for you is: your product is going to produce a prediction. Yes, this is cancer. No, it's not cancer, and it's going to produce a confidence in that prediction as well. So the question for you is: if the confidence is low, should the system make its diagnosis anyway, or should it defer to a human expert to make that choice? And that's another poll. So should we pop in
Right,
a moment?
except that I can't find the other poll is not coming up. And I don't know why.
You could bear with us for a moment.
It is there, but it's just not. It's not showing up, and I don't know why. Oh, for shucks.
I found it. I'll launch it.
Thank you.
So again, we'll just give you a few seconds to kind of look into this. And again, there is certainly an element of there being no right answer here. So don't worry about getting it wrong.
Okay, 5 more seconds. All right, ending the poll.
Let's see what we thought.
Okay.
Excellent.
Yeah.
So we have 7% said classify anyway. That's diagnose, sorry. Excuse me. And 94% said defer to a human expert. Which all, again, that makes a lot of sense to me. That my default intuition would be to defer to a human expert. I think it's interesting to think about why we think that though. Is it because we think the human expert is going to make a better job? Or is there an element of culture in there in that when we're not sure, we kind of would like a human to take responsibility for making a decision? I'm not sure it's necessarily clear-cut which it is. But again, depending on how you visualize the product, I mean, this could have been a product to support medical staff rather than direct to customers in different ways. So diagnosing anyway may have been the right answer if you were visualizing the product in a certain way as well. But yeah, obviously, like most of us, the default was we should get a human involved. So, okay, so I hope you enjoyed sitting in the product owner seat. So we've looked at machine learning models and building them and the challenges that are involved, and hopefully you've come to the conclusion that some of the intuitions are very straightforward and you understand a bit more than you did at the start of the talk. But you've also seen that there's some big challenges in there and some significant skill sets that would need to be involved to build your own machine learning models to put into the world in front of people, not just technical, but also in terms of ethics and harm and stuff like that. So I'm going to show you some ways that you can avoid some of those challenges. So some machine learning solutions that are available out there, and I'm looking at a Google product here called AutoML, although there are similar products in Amazon and Azure and other providers out there. What AutoML does and what similar products do is they basically automate that machine learning workflow to one extent or another. AutoML is quite interesting because it allows you to take an existing machine learning model that Google have built, say their image recognition model, so they can recognize a cat or the turnip, and then you can apply your own data on top to tune it a little bit. So if you imagine you had a natural language model that was trained on general natural language, and you were working in the medical domain, so you had some special terminology that you needed the model to recognize, you could take the general natural language model and then try and apply some more specific examples of your medical domain over the top. And that's called transfer learning. And this is the first product I've seen that actually kind of tries to bring that to a fairly general audience. I think AutoML is actually quite approachable. So if you are interested in that, I definitely recommend checking it out. there are lots of other products that can just automate the whole workflow from beginning to end as well. So without building on an existing model, you can just build your own model from scratch. If you look at the right-hand side, these products also actually deploy and run your model for you as well, and they'll provide you with the kind of metrics that show you show you about your costs and your performance in terms of latency and things like that. So most of those technical challenges can be taken away, and you're left with just the model building and model evaluation sort of skills required. But that may not be the best way to bring some awesome machine learning stuff to an existing product. So you can just take off-the-shelf models. So I mentioned Google has models for its for image recognition. So it has Google Cloud Vision, which can take. You can just show it an image, and it can recognize what's in the image. It can transcribe any text it sees in the image. It can give you information about the color schemes and palettes that are going to work with the image. There's similar products for videos to recognize objects in videos as the videos are playing. Translation, as I mentioned earlier, so you've probably all seen products that can do translation from one language to another by now. Transcription, so taking text, taking speech in the form of audio files and transcribing text. That technology is getting better and better all the time. All the way to dialogue, this is chatbots. So this AI and artificial and machine learning services that can help you build chatbots to interact with maybe customers on your website and to kind of screen out common queries and things like that. So all these things you can actually they're available as APIs. They're available to an existing product that you have. You can just call out to them and say, tell me about this particular thing that you want them to do. So you can introduce machine learning to your products without having to actually build your own models. And here's an example of the kind of thing we're talking about, going back to the Google Image API. If you go to the website, you can literally just upload a photo and click a button, and it will tell you what it can see in the photo. So in this case, I've uploaded a photo of a pair of gloves, and you can see at the bottom there, it thinks there's a glove and it's drawn, if you look, green bounding boxes around them. So it's showing you where in the photo the gloves are. The first glove, it's pretty sure it's a glove. It's 96% confident. The second one, a bit less sure, 95% confident. And they can tell you lots of other things about those images as well. But that's how easy it is to try these things out and get an idea of whether or not they're going to suit your use case. So that's what we did when I was working in a fashion startup in 2017. So we built an app which essentially you would take a photograph of yourself on the app. You could tap on an area of the photo and then tag that area with the clothes you're wearing. So you would tap an area of the photo, you would be taken to the retailer's website for that photo. You'd have to choose the retailer, go to the website, navigate to the products in the website, click save, and there's your tag. And then people who follow you can see what you're wearing, and they can go and buy the same clothes that you've got. We looked at our metrics and found that process of tagging up clothes was taking a very long time. It was taking people on average 40 to 60 seconds for every item. And we could see people dropping out of that funnel as well. They would start the tagging process and they wouldn't finish it. Understandably, it sounds painful, doesn't it? Tapping and typing in search boxes. So we wanted to try and make that better. So we looked at Google Cloud Vision. We could have used any of the other products out there as well. But we were already using Google Cloud for other things, so we used Google Cloud Vision. So we were looking at the clothing labels, the labels that you get on clothes when you buy them, to see whether we could scan barcodes. And that didn't work out because there's no publicly available, free database of barcodes, and we didn't want to. We wanted a quick proof of concept. But we noticed you could see lots of words and numbers on these labels. So we decided to try and do some text sort of match text scanning from the photos. So we updated our application to have a new tagging workflow for the retailers that we were trying. You would tap the button, you would tap the photo, and it would then ask you if you wanted to try and scan the barcode instead of navigating the website. You click go, show the label to your phone. We would then take a photo of the label, send it to Google Cloud Vision, get back any text it found on the label, and then match that up with the retailers that we'd implemented it for. And we found that we could then take you directly to the product page for that particular item of clothing. So we took a process that was very clicky, tappy, draggy, droppy typing stuff to a process that was basically hold your phone up to the label and is this the item of clothing that you're interested in? And you say yes or no. We put that in front of customers for a few weeks, and we found that 90+% of the time we took them to the right product. As in, we said, "Is this the product?" And they said yes. And we got some great feedback from that as well. People who had been using the product for a while and they were used to that long and drawn out process. They found it much quicker and much easier. And it went from something that was kind of tedious to something that was kind of cool. So that's just an example of how you can take a product, an existing product, and integrate some machine learning stuff without really doing hardly any of the work that you normally need to do. In fact, in this case, because it was just labels on clothes, we didn't even find anything particularly to worry about. We couldn't think of anything to worry about when it came to sort of ethical considerations in that area. And that it took us about a week to build that functionality and get it out into the App Store. So it can be very quick as well to go on this road, whereas building your own model is going to tend to be quite a long drawn out process. Just a quick update on that. So that was 2017. In 2020, Google does this automatically for you. When I showed my phone to this, showed this barcode to my phone, Google navigated me to the right piece of clothing. So, hey, Google took our idea. No, I'm sure they didn't. I'm sure they were doing it anyway. But yeah, that's quite cool. So, last words of warning on this. So even when using canned models, things can go wrong. So here's an example from when was this? 2015, I think. If you'd been using Google Cloud Vision for your application at this point, then some terrible mistakes could have been made, and people would see that as your product's problem. They wouldn't know that you were using a model underneath. So again, that's a way you could hit the headlines if you're not careful. So still a bit of care needed. And just to bring everything bang up to date, a researcher released a machine learning model for automated image upscaling. So, in old movies where somebody would have a pixelated image like this and they would hit an enhance button and it would get clearer. So we can do that now with machine learning. But that didn't quite work out the way many people would have expected it to. And this was covered in June 2020. So we can all see this is a picture of Barack Obama pixelated. If we use this pulse image upscaling model, that's not Barack Obama. And there's been lots of chat over the past few weeks on Twitter and on other platforms about how this kind of mistake happens relatively frequently in machine learning. Certain skin tones are recognized much more effectively than others. So there's lots of chat going on here. And I draw your attention to this particular talk. And we'll share a link to the slide so you can get back to this if you want to. There's a great three-part talk here, which is directly related to that last example on Harmon Ethics in machine learning. And with that, we're about done. So just to recap, we talked about why we do machine learning. We talked about machine learning workflow. We looked at linear regression and the k-nearest neighbors algorithms, and we showed you how those worked. We looked at the challenges you get with machine learning all the way through the process. You sat in the product owner seat for a couple of examples and had your say. We looked at cognitive and ML services as a way of making machine learning adoption easier. And we finally touched on ethics, bias, fairness, and harm in a couple of places in the talk. There's some resources available on the slide at the back of the slide deck here. If you do want to take your machine learning journey any further, you're more than welcome to have a look at these. And there's so many resources out there that you can use to take your knowledge to the next level with this sort of stuff. At the moment, it's such a hot topic. And with that, I'd like to just thank you all for listening to me and coming along. And thanks to Equal Experts for arranging and supporting the session.
Awesome. Thanks, Paul. We have about 10 minutes for questions. If you have a question, you can use the Q&A panel and pop it in there. And while I'm waiting for that, I may as well throw it in. Is there anything that you're interested in, Paul, that you want to apply machine learning to? Do you have a pet project that you're looking to try it on?
I don't really have a pet project at the moment. What I am trying to do is get up to date with the latest developments. I've let my knowledge kind of slip over the last couple of years with work that maybe a lot of work that wasn't involved with machine learning. So I'm trying to things like the Google AutoML product that I showed you earlier. I'm currently kind of reviewing Google's product set, because they're doing some interesting things, and I'll be looking at AWS's product set as well to compare. But yeah, I'm trying to get my skills up to date. But yeah, I should think about an interesting project, actually. That's a good point.
That probably is a good segue into your first question from Martin about how do you actually get into working with machine learning?
How did I, or how do you? I'll start with how I was kind of lucky, I guess. I I started learning about machine learning. I did a master's degree a few years ago, which gave me some of the groundwork. And then I just happened, essentially, there were a few little things in jobs I had that weren't directly machine learning related where I could use some of the techniques. So, for example, there was a project I was working on where it boiled down to a similarity problem. We had a bunch of attributes for people, and we wanted to recommend people to follow where they had similar attributes. And I kind of joined the team after they just started working on this and working on it for about a week or so, and they were building out a rule set to try and do this similarity analysis. But having done a bit of machine learning myself, I was able to come in and say, actually, this is a similarity problem. What we want to use is basically the k-nearest neighbors algorithm without the k-nearest neighbors bit. So we could use Pythagoras theorem, think of the whole thing as a space, and use Pythagoras theorem to work out how far away people were, pick the nearest ones, recommend those. So I think you can try and, if this is what you want to absolutely specialize in, you can just try and go for a role which is focused on machine learning. But you can always be keeping an eye open in whatever role you're doing today for problems that you might be able to use these techniques to solve.
Great. Unless we have any other questions pop up in the next couple of seconds, we might be wrapping up. Oh, here's one. From EZ, in which case machine learning generated content falls into, like the Barack Obama image enhancement? We've only got classification or regression. So when you were talking about your categorizations earlier.
Yes, well, that's a good one, actually. Is that... I think that's probably a regression problem, if anything, of those basic categorizations. Because if you think about it, the image is essentially a grid of pixels, which have different sort of color and intensity values. So if you want to, in the machine vision world, you have to find a way to take images and apply machine learning to them. So what people tend to do is essentially think of the images as just a great big long array of pixels. So basically flatten the whole thing out into one line of pixels. And then you can look at the similarity of each pixel to pixels in other images. So I think the nearest, I think what's probably going on behind there is a regression problem in that we're trying to predict the values for pixels in the sharpened image based on the values of the pixels in the coarse image, because those values will be numeric. They'll be 0 to 60 million or whatever, depends on the image format. But yeah, I think it'll probably be a regression problem kind of per pixel potentially, but there could be some classification mixed in with that as well. It depends on, you can blend these things, you can blend different models together essentially to kind of come up with sort of like an aggregate decision about whether to classify or what the regression value should be. So I guess you can have a blend of them, but I would imagine that regression is probably at the heart of that.
Cool. The next one is from Anthony Marta. It might be our last question. Do you have any opinions on the GPT-3 language model, which seems to have spawned much discussion recently?
Yeah, good one. These are great questions, by the way. Thank you. Yeah, so the GPT language model is so Elon Musk's OpenAI initiative, Elon Musk of Tesla fame. They came up with a language model that can generate text, and it generated a bit of stir in the media. I think it was last year when it was released, because it's very good. It can essentially produce snippets of text like you might get in a news article or a Twitter tweet. So these snippets, and they, at first glance, they're passable as a human could have written them. They're not terrible. Although as soon as they get to kind of several sentences long, you can generally sort of tell that there's actually no intelligence behind it. So I think that's the context of this question. I think a lot of it was just PR in terms of, like, this is what Elon's very good at, is kind of generating stir. I do think so. They refused to release the actual model itself. They released examples of what it was, and there were news stories about how it was game changing and it was dangerous because of what it could do in terms of impersonating people effectively, I think it was. I don't know. I think those claims are probably a little bit overblown, and but it is a big step forwards in terms of generating this synthetic sort of output. It's certainly one of the building blocks, and there were several other models in the same space as well that have made big strides recently. I don't think we're too far away from, I think like deep fakes is the current sort of term in vogue, I don't think we're too far away from it becoming very difficult to tell whether it's a video or text that's whether something actually came from the person it was supposed to come from, or whether it was completely invented and artificial, produced by an algorithm with a particular goal in mind. It's a fascinating time.
Scary stuff. All right, I think we are going to wrap up there for timing reasons as we're coming up to the hour. Massive thank you to Paul for getting up early for today's talk, and also thank you all for joining us. Hope you have a great night, depending on day or night, depending on where you are joining us from, and we hope to see you at one of our future talks. Thanks, Paul. Thanks, everyone.